Welcome there. How are you? I hope you are fine. In this video, I'm going to answer this exam. This is May-June 2025, paper 21. Of course, physics AS level. In the first paper, we have, of course, the data we need and some of the formulas we need. First question A. Define acceleration. Acceleration is the rate of change in velocity. The rate of change in velocity, not speed. The rate of change in velocity, or the change in velocity per unit time. Question B. In an experiment, two objects A and B are released from the side of a building as shown. Object A is released from rest at a height of 14 above the horizontal ground. Object B is released with an initial upward vertical velocity u of height at height 3.6 above the ground. Both objects take the same time to reach the ground, and they do not collide with each other. Air resistance is ignored. Calculate the time taken for the object A to reach the ground. Object A. Let's ask us a question: what we have and what we need. What we have is the distance or displacement. We have also the gravity 9.81. Initial velocity u equals 0. We need to calculate the time. Okay, so we don't have final velocity and we don't need it. So the suitable equation for this, that equation that includes everything except final velocity. So first one is S equals ut plus half at square. We need to adjust the equation or rearrange the equation to make t as a subject. Don't forget that u equals 0, so ut here equals 0. So s equals half at square. So we'll go directly, t equals the square root of 2s over a. Substitute equals the root of 2, s distance 14 divided by a 9.81. Equals, use the calculator, you will find it equals about 1.7 seconds. So this is the time, 1.7. Use your answer in B1, 1.7 the time here, to calculate u. U here is the initial velocity that for object B that being released. So let's ask the same question. What we have here for object B? We have the time now. We have displacement 3.6 and we have 9.81 as gravity. So what's the equation that includes all these variables? Of course, the same equation, S equals ut plus half at square. We need to arrange this equation to make u as a subject. Okay, u here has a value. Okay, so u equals, we will send this half at squared to the other side and divide it by t. S here minus half at squared and divided by t. We substitute s equals 3.6 the distance as we have here, or displacement, minus half a 9.81 t 1.7 squared divided by 1.7. It gives you the value directly. It's about minus 6.2 meter. Why minus? Minus because here's the direction of the initial velocity upward, but the object moves downward. So this is the direction upward. So U equals 6.2 meter per second, and negative here is just a direction of velocity which is upward. In a second experiment, object B is released from the same height and gives the same initial speed in A, but at release angle theta to the vertical, as shown in the figure 1.2. State and explain whether the time taken for object B to reach the ground is less, the same, or greater than the time in P1. We need here to see if the same time or less time as we calculated here, 1.7. The idea here, as the object released with an angle, it means the initial speed decreases. It means the initial speed decreases than this value that we calculated here, 6.2, which means less height. So less initial speed, which means less height. Less height will means, of course, less time required to reach the ground. Okay. Less initial speed, less height, less time needed to reach the ground. By considering energy, state and explain the effect of the change in release angle on the speed at which B reaches the ground. Here we are talking about the final velocity at B reaches the ground is by considering the energy. If we check here, the object is moving upward, then falls down. The idea here is the same energy, the same gravitational potential energy changes into kinetic energy because they are in the same height in both situations, whether B is projected upward, vertically upward, or with an angle. The idea here is the same displacement, the same height, 3.6 in both cases. 3.6, the same height, which means the same gravitational potential energy, which means the same kinetic energy, which means the same speed to reach the ground. So the same height, the same gravitational potential energy, the same speed. Okay, let's move to question 2. In question 2, A states the principle of moment. The principle of moment that when the object in equilibrium, the sum of clockwise equals the sum of anti-clockwise one. So right, when object in equilibrium, the sum of clockwise moment equals the sum of anti-clockwise moment. Three objects A, B, and C placed in a horizontal beam. The beam is in equilibrium as shown in figure 2.1. We have a beam. The beam is uniform and has a length of 6 meters. The pivot is at the midpoint. Object A has a mass 60 and it is at one end of the beam. Object B has a mass 45 kg and at distance x from the pivot. Object C has a mass of 80 kg and at the end of the beam. Calculate x. Here object in equilibrium, so the sum of clockwise C equals the sum of anti-clockwise A and B. So write the equation. M of A, moment of A, and moment of B equal the moment of C. Moment of A is the force times the distance. The force here is the mass times gravity. Force times distance of A and force times distance of B equals the force times distance of C. The force of A is the mass times gravity, 60 times 9.81, times the distance, here is distance, half of 6 equals 3, plus 4B, mass of B, as you see here, 45, times 9.81, times the distance, which is x, equal the force of C, the mass of C is 80, times 9.81, times distance, also 3 here, half of the rod. We arrange the equation to find x. We'll send 60 times 9.81 times 3. We can cancel 9.81, 9.81, 9.81 here. 6 times 30, sent to the other side. 60 times 30, 180 in negative to the other side. 80 plus 30, 200. 80 plus 3 equals 240. Minus 180 divided by 45 gives you the answer 1.3333 meters. According to, we approximate the number, and according to significant figures, we have only two significant figures here, so the answer will be 1.3 meter. C. The beam is 0.8 above the horizontal ground. Object A is removed and replaced by a spring connected to the ground and the beam, as shown in figure 2.2. After the change, the beam is assigned horizontal and equilibrium. The position of B and C are unchanged. As we removed object A, so the moment which was clockwise, so there is a, of course there will be an extension in the spring. He gave us the new length of the spring 0.8 to keep the equilibrium. The spring has a stretched length of 0.59 and obeys Hooke's law. Calculate the spring constant of the spring. To calculate the spring constant, we need the force and extension. Extension, we have it here. We have unstretched length 0.59 and we have the stretched length. So x equals 0.8 minus 0.59 equals 0.21 meter. For the force, is the same force of object A. It's the same force of object A. Force here equals m. We have the mass and the gravity. Mass of object A, as mentioned here, 60 kilograms. So 60 times 9.81 equals 588 Newton. Now we have x and f. We can calculate the spring constant. K equals f over x equals xf, as we calculated, 588, and the extension 0.21 equals 2800 Newton per meter. Newton per 2800. Calculate the elastic potential energy of the spring. Elastic potential energy E equals half kx square or half fx. We have everything. I have kx square or fx, or kx square or fx. Let's use this equation, half kx square. So it equals half k, we calculated 2800, x, as we have it here, 0.21 square, gives you about 61.74 joules. So the final answer, approximating and according to significant figures, we have two significant figures here. So the answer will be 62.